Welcome to this video on enlargements and stretches using matrices. So first of all, just the two words. So enlargements, so an enlargement is like enlarging by a scale factor, like 3 times the size, scale factor 3, half the size, scale factor a half, and it affects both the x and the y coordinates equally. Now, a stretch is when you enlarge the x coordinates and the y coordinates differently. Like if you say enlarge the x coordinates by multiplying them by 3 and enlarge the y coordinates by multiplying them by 2. That would then be stretches instead of an enlargement. So enlargement affects both the x and the y equally, and a stretch affects them differently, separately. Sometimes it could just be a stretch in the y or stretch in the x. Now, a transformation of these types is represented by this matrix, okay, where A and B can be any value. Okay, so A represents a stretch parallel to the x-axis, and B represents a stretch parallel to the y-axis. And when A equals B, when they're the same size, it's an enlargement. Okay, scale factor A. So it's an enlargement. And then it's the different things. So like if B equals 1, then it's only a stretch in the x-axis. And if A equals 1, it's only a stretch in the y-axis. Now, in terms of invariant lines and invariant points, you just have to kind of think these through. So the invariant point, or one that's always an invariant point, is the origin. Okay, and invariant lines, the x-axis and the y-axis, they will be invariant lines, but they won't be invariant points on those lines. So if it was a stretch parallel to the x-axis, then points on the y-axis would be invariant points, and any line parallel to the x-axis, including the x-axis, will be an invariant line, but not invariant points, because they're the ones that are being enlarged. And vice versa, a stretch parallel to the y-axis would mean that the y-axis and any line parallel with the y-axis will be an invariant line, and points on the x-axis are invariant points. Okay, but if there's stretches in both directions, you'll have invariant lines and only the origin as the invariant point. Now, when we previously looked at reflections and rotations of 2D shapes, they both preserved the area of the shape. Okay, when a shape is now stretched, its area can increase or decrease. Now we can use the determinant of the matrix to work out the scale factor. Now, for a linear transformation, which is what we're dealing with, okay, the determinant of that matrix represents the scale factor for the change in the area. So not the change in the length, the change in the width, but the change in the area. It's sometimes called the area scale factor. Now, if the determinant of the matrix happens to be negative, it just means that the shape has been reflected. Okay, so don't worry about, a negative sign. Much like at GCSE when you enlarge by a negative scale factor, you know, like enlargement by -2, scale factor -2, the shape would end up twice as big, but it would be the other side of the point of enlargement, if you can picture that and remember it from GCSE. Okay, well, that's enough initial talking from me. Let's look at a couple of examples. Okay, so here is our example. We've got matrix M here, and the first one is to describe fully the transformation represented by M. Okay, so the matrix is of the form A0, 0B. So, you know, A0, 0B. It's of that form. So it has a stretch parallel to the x-axis of scale factor 3, and then it has a stretch, so and a stretch parallel to the y-axis of scale factor 2. Sorry about my writing. I'm making this video in my Easter holidays, and having not used my hands to write for a while, it's it's all going a bit weird. Anyway, that is part A done. Now, part B, triangle has these vertices, find the area of the triangle. So I didn't need to draw this triangle, but I've done it just to be a little bit visual. So base of 1 and a height of 3, so right angled triangle. So half times base times height. So 3/2 or 1.5. Right. I do apologise. Well, you can't hear because I'm kind of going off camera, but I can't stop coughing at the moment. I've got a terrible cough. So hopefully, even though I am kind of pausing, cutting and doing a lot with the audio and stuff, hopefully it's still coming across okay for you guys. Now, part C, the triangle is transformed using image on matrix M. Find the area of the image. Now, obviously there is a quick way to do this, but I just want to show you the transformation of the triangle and then have a look at the area in kind of two ways. So that's my transformation matrix, and these are my coordinates. And these are the coordinates I've ended up with: 6, 0, 9, 0 and 9, 6. So here we have it, the original triangle and the new triangle, the enlarged one, the stretched one. It's been stretched by a scale factor of 3 in the x direction and 2 in the y direction. Now the area of this shape is a half times 1, 2, 3 times 6, so 9. Now obviously I wouldn't want to have to do this, you know, all the time. So let's look at how we can go about doing this in another way. So I'm just going to do this over here in purple. So this is my matrix M, and I'm going to find the determinant of M. So that's 3 times 2, which is 6, minus 0 times 0, which is 0. So this has a determinant of 6. Now that is the area scale factor. So I take the area of the original multiplied by the determinant. So 1.5 times 6 equals 9, which is exactly what we had when we did it the long way. Okay, so that is how I can use the determinant to find the area of my transformed shape. And with that, I think this is quite straightforward. So we'll get into some questions, and as always I'll go through the answers at the end of the video. Don't forget to like if you're finding this video useful, subscribe if you haven't done so already and you want to kind of see more of my videos or you find them useful, and if you're a long time viewer or you want to just help me out a little bit financially, then consider joining. Okay, you don't get anything for joining as such, you know, it's just a way of giving back to me if you are so inclined. Anyway, let's look at the questions. So here we have 3 questions. They're all past exam questions. Obviously, you know, not a full exam question, but just taking bits from past exam questions that just deal with the enlargements and the stretches. Okay, so 3 questions, and as always I'll go through the answers at the end, so pause the video anytime now. Okay, so here is the first one. So we're describing it, so stretch parallel to x-axis, scale factor 2. And then we've got a stretch parallel to the y-axis, scale factor -3. Just reading those 2 values off, you know. 2D shape with area K is transformed using M. Given that the image has an area of 24, find K. So let's find the determinant of M. So it's 2 times -3, so -6 minus 0, so -6. And then let's look at the area. So we've got the determinant of M multiplied by K equals 24. Now, because the negative sign here, the negative sign of the determinant just means it's a reflection, then all I need to use is the positive one just to find the area. So 6 times K equals 24, so K equals 4. Okay, and that's all there is to question 1. Okay, question 2. Describe fully the transformation of matrix A. Now, in this one, both A and B are the same size, so it's not a stretch, it's an enlargement. Enlargement of scale factor 2√5 from the origin. Okay, they're linear transformations. They're all the enlargements are from the origin. Triangle has coordinates A1, 4,1 and 4,3. Given that the triangle is transformed using matrix A and the new area is 60, find the value of A. So first let's work out the determinant of A. So it's 2√5 times 2√5 minus 0. So that's 4 times 5, so that is 20. So if we use K as the area of the original triangle, 20K equals 60. So K would be equal to 3. So the original triangle has an area of 3. Now looking here, 4, 1 and 4, 3. Now if I just a rough sketch, here is 4. So this would be at 3 and at 1. And this would be A. So as a height of 2, an area of 3, so it needs a base of 3. 3 times 2 is 6, divided by 2 is 3, which is what we want. So A would be 1, or we could equally go the other side of the 4, add 3 on, that would be my A that way. So 1 and 7 are our two possible answers there. Okay, hopefully that makes sense. Okay, third and final question. Right, we've got to find M2. So P1, PQ times by P1, PQ. So that's P squared plus P. And then we've got P plus Q. We've got P squared plus PQ. And P plus Q squared. Now, part B. M2 represents an enlargement of scale factor 6. Now, I can start by finding the determinant, but that's obviously very complicated. But remember that this is what we should have, isn't it? So if it's an enlargement of 6, then these values would be 6. And this should be equal to this. So P squared plus P equals 6. P squared plus P minus 6 equals 0. This is going to be 2 and 3. That'll be negative, that'll be plus. So P equals 2 or P equals negative 3. Now, if I look at the next easiest one with P and Q in, this one, or this one I should say, equals 0. So P plus Q equals 0. So Q equals negative P. Now, I know that Q should be positive. So that would mean that Q is negative P. So if P is 2, Q is negative 2, which would mean it's less than 0. So P must be negative 3. So that means that Q equals 3 and P equals negative 3. And that's how I find the answers there. And I use that one because if I'd used this one, I've got P and Q squared. And it's a quadratic, which is going to give me two possible answers for Q. But also P is currently two possible answers, and I don't know which one's correct. So that's why I use this linear one equaling 0. Okay, so hopefully that makes sense, and hopefully this video provided you with, you know, a little bit more insight into the transformations. The next video now will be successive transformations, so when we're combining transformations in one or more matrices. Okay, so stay tuned.